happens when they have a bar, then you redistribute angular momentum and energy all the time. So all of these kind of features of minima can easily disappear. So yeah, it's a self-interacting dark matter. So that's just simply I thought. Yeah, we had a, one thing is, do you now believe that after Frank's talk, do you now believe that self-interacting dark matter is ruled out? Or is anyone still in favor of self-interacting dark matter? Are you in favor of self-interacting?
Yeah, I think what Frank showed with this off-centered AGN, these are, it's not a quantitative analysis yet. So.
Good. So now here are the questions, and maybe look a little bit at that. I hope you can read them. So we basically had 3 sections: dwarf galaxies, dark matter halo properties, stellar feedback, galactic winds. Maybe start with dwarf galaxies. Can we make reliable predictions for the abundance of satellite galaxies, especially at small halo-centric radii? Is there still a cold dark matter substructure problem? And how can we find evidence for completely dark halos? So if you want to discuss any of these 3 questions.
So I actually have a specific question for maybe the observers. What do we know about the radio profile of satellite galaxies, observationally? I know that in clusters, it seems to be perfectly consistent with the NFW profile. There's been a lot of work with Sloan data and stuff, but it's always, the damn fiber collisions that make it very hard to probe inside. So I'm wondering whether there's anyone who knows about any updates, more reliable work about the radio profiles. Are they cored or not? I think that's where really, we're struggling to get things right in the simulation.
Sorry, are you asking about what's the radial profile of the dark matter halo of a luminous galaxy?
No. What is the number density profile of satellite galaxies in their host halo? Does it basically follow an NFW profile, or is it really cored in the central region? Do you see a clear indication that the central galaxy destroys dwarf galaxies or any of those things? Even with Saga, it's really
so I don't with Saga, there's like 300 satellites if you add them all up. And the galaxies are slightly different. So the one thing that I'll say with Saga is that the one thing that's very clearly demonstrated, which we did say in the paper but perhaps is not emphasized strongly enough, is that there's a difference between the quenched and the star-forming satellites. The quenched satellites are more centrally concentrated. So the population is not uniform, and presumably evolutionary processes have been affecting that.
And we've done something similar with Bayesian statistics of large samples of satellites in Sloan, and what we sort of infer using also satellite kinematics is that the data is consistent with a profile that is sort of NFW-like, but it needs to have a scale radius is about twice as large as you expect for the dark matter. But it's very hard to tell the difference between cuspy and cored in the central regions. And,
But Frank, why do you think it should follow NFW? We know from simulations in our 17 paper, right? There is a bias function, almost a universal bias function between the satellite profile and the smooth dark matter profile. And this how strong the bias is depends on the mass cut you apply to the satellite population. If you can resolve, we talk about the bias or a profile that is shallower than the smooth halo when we focus on, say, bright dwarf satellites. But if you can, observationally, if you can probe down to Earth mass, then the profile must be, according to lambda CDM, there must be more cuspy than NFW because of dynamical friction.
Well, let me tell you why I think there's still something that I certainly don't understand. If you look in existing simulations, dark matter only, let's keep it simple, and you look at the radial profile of subhalos, it does not correlate at all with the instantaneous subhalo mass. You see no indication of mass segregation. So it's not that the more massive subhalos are further out and the less massive subhalos are further towards the center. You sort of seem to argue that that's what you would expect, and I agree with you that that's what we'd expect, but you don't see it in the current simulations. Now, we know that the current simulations have all these problems with subhalo finders and all And ultimately, the only way we're going to probe this observation is by looking at satellite galaxies. So that's why I'm interested in all this stuff.
I was going to comment that this is one from total ignorance, but I realize the resolutions aren't good enough to tell how many globular clusters are going to form, et cetera, et cetera. But if you could do that, would globular clusters in principle provide enough information, or for some reason they're not adequate as a probe of the inner regions of, because there's many more of those that you
I'm not interested in finding a probe of the inner regions. That's not what I'm interested in.
Globular clusters are many more than anything else you can do.
Yeah. So in principle, you could use them as a probe and do dynamics with them and probe the central dynamical, test whether the dark matter has a cusp or a core. That's what I'm talking about.
Yeah.
I want to know what the number density of satellites is doing. And this relates to the work that Ethan is doing, right, where you're trying to measure how many satellites does the Milky Way have. Can we now use this to constrain the nature of dark matter, warm dark matter?
My question is simpler. Are globular clusters eligible as what you call probes or not for some reason?
Probes of what? That's my
Probes
question.
of profile.
I want to know what the number density profile of satellite galaxies is in host halos like the Milky Way.
Do globular clusters count? No.
So I didn't use the word globular clusters. I'm not interested in globular clusters.
So no, the answer is no. Okay, so Martin, you had it not. I think we should move a little. Always dark matter. Let's go to something which has some stars and some winds in it. So let's go to dwarf galaxies. We had a lot of discussions on outflow, and one question is, of course, outflow doesn't mean it's escape. It's just simply moving out from the inner region and maybe falling back. So the question is there evidence for real escape, or is it only evidence for pushing gas out? And the gas could fall basically in and restart star formation, or what do we know, and refuel the center. And what is your opinion about this? How likely is it that you can really have gas escaping the galaxy, the dwarf galaxies? And are there some questions about that, or some discussion about that? Yeah.
Ignorance question. Have any simulations gone through a long enough period of time with the dwarfs to see several cycles of quenching and then rejuvenation? Or do they always find that after one event that things just stop? I'm just asking a question here. I don't know. Have any idea? Do people think to stop after an event?
No. So, yeah.
No one wants to comment?
Yeah, well, people have to think about it, of course.
I mean, yeah, if the question is, do we see that, then yeah, absolutely we do. And how strong that effect is or how common it is somewhat fairly mass dependent. But we see instances of bursty star formation followed by periods of quiescence and then rejuvenation, and that kind of, I guess it's hard to quantify how closely that tracks with the gas recycling, right? But we also see in the spatial extent of the gas that it's being, some of it gets blown out and then some of it falls back in on some time scale. And those time scales tend to be mass dependent too. I mean, that's a good question, and I guess part of it is that it's hard to measure star formation histories as precisely as you can see them in the simulations, right? And I personally think that's one of the reasons that the kinds of star formation histories we can measure in the local group are so valuable, because you can get fairly small time sampling there. And there's, of course, issues associated with how those are measured, but part of the problem currently in the local group is that we don't really have that many gas-rich star-forming satellites. Right?
So you want to find theoretical evidence which you can then prove with observations. that there's outflow where there's or escape.
Right.
And probably doesn't seem so. Otherwise, people would say yes. There's evidence. Just if you have a question, just simply raise your hand. If not, then I pick a question, or Frank picks a question.
I think an interesting link to the little red dots that we had earlier in the week, where we see broad emission line, and that's often been interpreted as evidence for AGN. And I thought it was interesting to see this talk this morning about the broad wings in the winds, and nothing to do with AGN. So, anyone wants to have that? Does anyone know of anyone having looked at whether the broad wings in the LRDs might be winds? Is there a way to test it?
Difficult. No one.
Or do we need huge amounts of star formation to produce those winds, and unless we see that star formation, which we don't seem to see in these things, we can rule it out? Or might the star formation be hidden from view? Like dust.
Good.
For some little red dots, like you usually see some like blue shifted dip in the broad wings, for example, in perpendicular line like H alpha. And interestingly, like if you compare their broad wings shape and also those blue shifted absorption like to, for example, Eta Carina's like spectrum, you see very similar features. So someone might wonder whether those blue shifted dip is like just purely due to like P-Cygni profile.
Yeah. But we do expect large, copious amounts of star formation to drive those winds then, right? Is there any way we could reconcile LRDs with copious amounts of star formation, keeping it out of view by dust or something? Or is the SED completely inconsistent with that? Very dusty star formation. Come on, anyone must know the answer.
I don't know the answer for certain. I think that some of the literature around little red dots says sort of, if it was something we would expect blah, which in this case is far infrared luminosity, and then you don't see blah, so it's not that. You don't have a Miri detection of little red dots. And it's unclear whether that's totally legitimate, I mean, I'm not speaking specifically about that, but for all the causes of little red dots, there's always, there's always some inconsistency, and it's because they might be a somewhat heterogeneous population and so on and so forth. So I think some of this is that we just don't know. The other thing that I would say about this is that it would be really nice if we had like absorption line probes of the outflows from little red dots, and I don't think, I'm not up and on the literature enough to know, but if we had that, then I think we'd know more about the nature of the wind, but I don't think we have that yet. Because they're really faint, so it's hard to get things like, the absorption line profile. And there's also like, are we observing them at the right wavelength?
I'd like to ask Ben maybe, given I don't work in little red dots, but I know that if you could stack up a huge amount of data, so you just pick up the emission line, is there any evidence or possibility of getting evidence the extent to which emission lines are observed relative to, say, the continuum that's observed? Does anybody work in this area to know if that's a crazy idea? I mean, when I work in a region where we have very little information, so we do what we can to get very faint things. Is that something worthwhile to do? Because you guys have emission lines and you have continuum. And I'd love to know with relative size distributions of those two components, that might be a clue as to whether they're winds or whether they're symmetric, etc.
So, I think it's a suggestion you should keep in mind. I was wondering about mass loading factors of the winds, and how do we really measure them? And especially what I found interesting, if you have cold material, dense material in the winds, is this actually molecular gas that was in the disk being blown away, or did it form in the wind by whatever shock forms or whatever. So do you really know this is blown out molecular clouds of the galactic disk? What do we know about this? And yeah, how is the mass loading factor dependent on whether you have a fast wind with broad emission lines or whether you have a very kind of slow wind, which is actually then maybe not really a wind, but it might fall back again. So is there dependence of mass loading on the velocity of the winds? What do you know about that?
I was just going to say, I think on the
molecule part, this has been studied in like the Mercurian-231 winds in particular, where you have these couple thousand kilometer a second molecular winds. And that's very hard to explain the presence of molecular gas. And there was nice work
closer. Yeah, a little closer.
There was nice work by Alex Richings and others showing that you could reform the molecules even as they were dissociated in this, but their big catch was you still needed, that only works in the time scale of the wind expansion time if the winds are dusty, and you can catalyze molecule formation on the dust grains, which sort of moves the question to how would dust grains survive a couple thousand kilometer a second wind. And I don't have a great answer, but I think it's, relates to some talks we had in the first couple days of this meeting, where there's a growing number of suggestions of sort of dust survival in CGM and other environments where we normally assume dust shouldn't exist. So maybe these are all linked problems, but there's more work needed, I think.
Yeah, and I think related to that one is the stripping, right? We see cases where people see these beautiful tails of material that's being stripped in coma clusters, and you see molecular gas there and dust there, and is that lifted out of the disk, or is it sort of formed in these tidal tails? And I think the jury is still out on that, and hard to imagine either.
Yeah, I think Peng and his student. Yeah, usually you think like the density contrast between molecular gas and hot wind should be so high, so they should be destroyed within the wind. But I think Peng and his students Ray has a paper earlier this year like discussed that dust or molecular gas can be like protected by a ionized gas to a 4K. So they can be like the density contrast between the cold gas at 10 to the 4 to the 10 to the 6K hot gas, they just around 100. So they can be survived within an ionized gas shell. And those dust can also grow, and the molecular gas can also survive there.
So maybe one last question, Frank? You want to ask one?
Was that it?
Yeah, well, yeah, go on. So okay, if I'm allowed to pick one, I'm not ready. I was never really worried about this 8%. Why only 8% of gas in the universe is in stars? This is connected to me to this inefficiency thing, and so I just wondered, is there really a problem? Now it was brought up, and I got really worried. Maybe there is a problem, or do you think this is more or less understood by the fact that lots of gas sits in galactic halos and is not really falling into galaxies, and what falls into galaxies then is very inefficient in star formation. So for me, there wasn't a big problem, but maybe there's indeed an interesting problem. Maybe one can discuss this at the very end. And the inefficiency of star formation, I thought is also kind of now more or less understood, but maybe not. So where do you see, where do we need to make more progress for deeper understanding?
I think we need to understand the redshift evolution of it.
Yeah,
now all this new evidence of high redshift, it's not an 8% efficiency, but a much higher. And
oh, this is only an idea. It's not yet proven, isn't it?
yeah.
So, yep.
I'll just say one thing, which is that I think people use star formation efficiency for two different things. One of them is how many stars do you get out of a giant molecular cloud, and that's a few percent. And by mass, the mass ratio. And then the other is, what is the mass ratio, you know, in that plot where you have the mass spectrum of the dark matter halos and the mass function of galaxies, and then, you know, so that plot, and there you have something that is itself a function of mass. And those aren't the same thing. They're undoubtedly related in some sense, in that it's harder to get, you know, gas into stars than, you don't just collapse something and turn all the gas into stars. But they're not the same thing. So you know, if you crammed gas into the galaxy, and even though it only forms 1% of every molecular cloud into stars, if it all just sat there forever, eventually it would turn into stars. So there's still some, you know, question about keeping, if you put the gas in the CGM, how are you keeping it there, et cetera.
Okay. If there's no more questions, then I think, Frank, if you agree, because I'm really hungry, I have to say. So let's go and have a nice lunch.
So so it's sort of a barbecue thing. The different dishes have labels by them on the table specifying which things are gluten-free, vegetarian, vegan. They did say the potato salad uses vegan mayo, so that's also vegan, just so you know.